Modes of heat transfer. Heat can be transferred in three basic modes: conduction, convection and radiation. All modes of heat transfer require existence of a temperature difference. Conduction. In case of gases, the transfer of energy from more energetic articles of a substance to the adjacent less energetic ones as a result of interaction between the particles. So you can see that in gases and in liquids, conduction is due to either collision or diffusion of the molecules during their random motion, whereas in solids it is due to the combination of vibration of molecules in the lattice and the energy transport by the free electrons. It is combination of these two phenomena. You can see here for solids the molecules are closely in touch with each other, whereas the same is not the case with the gases or the liquids. Here in case of gases you can see the molecules are very far from each other, right? In conduction, you can see I have shown a slab over here. Heat conduction through a large plane. Wall thickness is given by delta x and the area is A. Now, as I said, without temperature difference there will not be any heat flow. So here the heat flow shown is Q and the temperature difference is like T1 is not equal to T2, and you can see that the heat transfer direction is given in the x direction. So the rate of heat conduction through a plane, you can say it is proportional to the temperature difference across the layer and the heat transfer area A, but it is inversely proportional to the thickness of the layer, that is delta x. That means if delta x is less, heat transfer rate will be more. So I can equate it like this: rate of heat conduction is directly proportional to area into temperature difference divided by the thickness. So if I take the equality sign, you will have a constant which is K, and that K is our thermal conductivity. Capital A is the area of that plane. T1 minus T2 is the temperature difference and delta x is the thickness of that slab, which is equal to minus Ka dt by dx. Now you will wonder why minus. Heat will always transfer in x direction, and it will transfer in a direction where the temperature is decreasing. Say I'll say T1 to T2. T2 is always less than, T2 will be less than T1. So if you want to take temperature difference, right, so it will be T2 minus T1. So that is why this minus sign, where delta T by delta x is called thermal gradient. So Q conduction is equal to minus Ka dt by dx. So thermal conductivity K is nothing but measure of the ability of a material to conduct heat. You can see here two examples I have given, one for copper and one for silicon. Copper, you can see the heat transfer rate is high, 4010 watt per meter square. Temperature is same, thickness is same. Temperature T1 is 30 and temperature T2 is 20. Whereas silicon, see the thermal conductivity K is 148 watt per meter Kelvin. Same conditions, the T1 temperature is 30, T2 temperature is 20, thickness is 1 meter, but see the amount of heat transferred is 1480 watt per meter square. So thermal conductivity does influence the rate of heat transfer. As I explained you before, temperature gradient, it is nothing but the slope of the temperature curve on Tx diagram. As I said, the heat flux will always move in the direction of the lower temperature or the decreasing temperature. Heat is conducted in a direction of decreasing temperature, and the temperature gradient becomes negative when the temperature decreases with increasing x. Negative sign in the equation ensures that heat transfer in the positive x direction, it's a positive quantity. Capital A represents the area which is normal to the direction of the heat, and rate of heat conduction through a solid is directly proportional to its thermal conductivity.